Welcome to the Explainer. All right, today we're going to tackle a really critical but sometimes confusing step in machine learning, feature scaling. We'll break down the two heavy hitters, standardization and normalization, and figure out what's what. So here's what we're going to cover. First, we'll look at why we even have this problem in the first place. Then we'll dive into standardization, then normalization. After that, we'll talk about a special case, those pesky outliers. And finally, the main event, how to choose which one to use.
Okay, first things first, let's really get to the heart of the issue. Why do we have to go through all this trouble of scaling our features anyway?
I mean, it's a weird thing to think about, isn't it? As humans, we get the context, but an algorithm, it's just looking at raw numbers. So why would it get so distracted by the size of one number over another? And this right here just lays it all out. You've got age at 45 and salary at 90,000. To a machine, 90,000 is just gigantic compared to 45. That massive difference in scale can completely unbalance the whole model. And here's where the real trouble starts. A lot of models work by measuring the distance between data points. When that happens, the salary feature just completely takes over the conversation. It dominates the math, and suddenly age looks like it barely matters at all, even if it's super important for your prediction.
Okay, so that's the problem. How do we fix it? Well, let's bring in our first solution, standardization.
Now, what standardization does is pretty clever. It's not just about making numbers smaller. It actually repositions your entire dataset so that it's centered right around zero, and it gives it a nice, consistent spread.
And the formula might look a little intense, but it's actually super straightforward. For every single value, that's your x, you just subtract the average of all the values, that's the mu, and then you divide by the standard deviation, that's the sigma. Simple as that. To really get a feel for this, picture your data as this cloud of points floating in space. The first step, mean centering, basically grabs that whole cloud and drags it so its center is sitting right at the origin, at 0. Then, unit scaling kind of zooms in or out on the cloud until its spread is exactly 1 in every direction. And what's really key here is that the original shape of your data doesn't change.
All right, on to contender number 2. This one takes a totally different approach. Let's talk about normalization.
Yeah, this one's a whole different animal. Forget about centering the data. Normalization is all about, well, squeezing it. The goal is to take every single data point you have and force it to live inside a very specific range, usually between 0 and 1. And again, the formula tells the whole story. All it's doing is asking a simple question for every single data point. How far are you from the absolute minimum value as a percentage of the total range from minimum to maximum? So what you end up with is this perfectly neat little box where all your data now lives. Everything's between 0 and 1. Sounds great, right? Well, there's a huge catch. Because the minimum and maximum values define the boundaries of that box, this method is extremely sensitive to outliers. And that brings us to a really, really important issue. What do you do when your data has those extreme values, those outliers, that just don't follow the crowd? You have to ask this question because just 1 or 2 of these rogue data points can completely throw off your scaling and, in turn, really hurt your model's performance. And here's the bottom line. Neither of our two main techniques are all that great with outliers. With standardization, an outlier is still an outlier. It's just on a different scale, still far away from everything else. But normalization, oh boy, it can be a disaster. One really high value can squash every other data point into a teeny tiny little range near 0, pretty much wiping out all the useful information. So what do we do? Well, luckily, there's another tool in the toolbox called robust scaling. It's designed specifically to handle this exact problem, messy, real-world data with extreme values. See, instead of using the mean and standard deviation, which, get totally pulled around by outliers, this method uses the median, which is just the middle value, and the interquartile range, or IQR. The IQR is just the range that the middle 50% of your data lives in. By focusing on the bulk of the data, it basically ignores those crazy outliers at the end. Okay, it's time for the main event. We've seen the techniques, we know the risks with outliers, so how in the world do you actually pick the right one for your project? This is the million-dollar question, isn't it? And the answer, as you've probably guessed if you've been in data science for a while, is, well, it depends. But it depends on things we can actually figure out. And this table right here is your guide.
You should lean towards standardization if your algorithm is based on distance, or if it assumes your data looks kind of like a bell curve, which is true for a lot of neural networks. Go for normalization when you know for a fact what the minimum and maximum values are, like for image pixels that are always 0 to 255. And if you even think you might have outliers, just start with robust scaling. It's your safest bet.
And this is just as important, knowing when you even need to do this at all. For models like KNN, PCA, and neural networks, scaling is absolutely critical. They just won't work well without it. But then you have tree-based models, like decision trees or random forests. They couldn't care less about the scale of your features because of how they work, so you don't need to bother.
But at the end of the day, there's no substitute for just trying things out. Seriously, machine learning is an experimental science. You can't always know ahead of time what's going to work best. So try a couple of different scalars, see how your model performs, and pick the winner.
Look, what we're really talking about here isn't just some math trick. It's about fairness. It's about making sure every feature in your dataset gets a fair shot to tell its part of the story, without the features with big numbers just shouting over everyone else. So now that you know how to level that playing field, what story is your data waiting to tell you?